Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you very much. I'm Philip Emeagwali. I'm an extreme-scaled computational algebraist. Extreme-scale algebra is the recurring decimal in the discovery and recovery of otherwise undiscoverable and unrecoverable crude oil and natural gas. The massively parallel processing supercomputer is the bedrock technology that must be used to discover and recover crude oil and natural gas. My invention of the massively parallel processing supercomputer that occurred on the 4th of July 1989, that was recorded in major US newspapers and recorded in the June 20, 1990 issue of the Wall Street Journal, opened the path to excruciatingly detailed computational physics, such as extreme-scaled petroleum reservoir simulations. My invention of the massively parallel processing supercomputer changed the way we solve the toughest algebraic problems arising in extreme-scaled computational physics. My invention of the massively parallel processing supercomputer inspired a new way of high-performance supercomputing. My invention of the massively parallel processing supercomputer enabled computational mathematical physicists to compress their time to solution from a theorized 30,000 years to just 1 day. My invention of the massively parallel processing supercomputer led to a paradigm shift in high-performance supercomputing. In the old paradigm, the high-performance supercomputer was computing sequentially or solving only one algebraic problem at a time. In my new paradigm, the high-performance supercomputer is supercomputing in parallel or solving 1 million algebraic grand challenge problems at once. The fastest algebraic computations of the early 1980s were executed on vector processing supercomputers. Those vector processing supercomputers operated on pairs of lists of numbers. Executing floating point arithmetical operations on pairs of lists of numbers is an order of magnitude faster than merely operating on pairs of numbers. That ability to execute floating point operations on pairs of lists of numbers inspired the invention of the cyclic reduction algorithm. That algorithm can be used to solve a system of tridiagonal equations of algebra and solve them with shorter times to solution. The cyclic reduction algorithm. The cyclic reduction algorithm is slower on sequential processing supercomputers. The cyclic reduction algorithm is faster on vector processing supercomputers. The reason the cyclic reduction algorithm is faster on vector processing supercomputers is that it takes advantage of some parallelism introduced by the cyclic reduction algorithm and introduced into the set of floating point arithmetical operations. For the cyclic reduction algorithm to work, the matrix must be diagonally dominant. That matrix is the array of the coefficients of the system of finite difference equations of extreme scale algebra that I formulated and that arose from my discretizations of the governing system of partial differential equations of modern calculus that I invented, that is called the Philip Emeagwali equations, that arose from my encoding of a set of laws of physics that governs the motions of the crude oil, injected water, and natural gas that is either simulated across an isolated processor or across an ensemble of processors. The matrix is diagonally dominant when the diagonal entry of the matrix is at least equal to the sum of the two off-diagonal entries of the same matrix. The cyclic reduction algorithm requires the execution of more floating point arithmetical operations. The trade-off is that some of those floating point arithmetical operations can be speeded up and operated as pairs of lists of numbers. One reason the technology of parallel processing was scorned, ridiculed, and rejected by Seymour Cray and Gene Amdahl, and ridiculed by the community of 25,000 supercomputer scientists of the 1980s, and dismissed by everybody as a huge waste of everybody's time, was that it was truly a waste of time to attempt to solve a system of equations arising in extreme scale algebra that possessed non-zero, non-diagonal entries, and in particular, to attempt to solve those algebraic equations in parallel. It was truly a waste of time to attempt to solve those algebraic equations by processing many things or processes at once. However, for excruciatingly detailed crude oil and natural gas reservoir simulations, I invented how to reformulate those algebraic equations and how to reformulate them from first principles and reformulate them by re-examining the foundational calculus and the foundational physics from which those algebraic equations arose. In a nutshell, the 25,000 supercomputer scientists of the 1980s demanded lockdown evidence that they could massively parallel process across a new internet that is a global network of 65,536 tightly coupled commodity processors that shared nothing between each other. I, Philip Emeagwali, won accolades from supercomputer scientists because I provided that lockdown evidence, and I provided that evidence on the 4th of July 1989 in Los Alamos, New Mexico, United States. Over my first 60 years of supercomputing, that is onward of June 20, 1974, I gained practical supercomputer knowledge, namely the deeper understanding that the toughest initial boundary value problems arising in extreme scale computational physics were not defined by the system of partial difference equations of extreme scale algebra that govern those problems. The toughest problem in computational physics was defined by the laws of physics from which the initial boundary value problem of calculus that governs, say, a general circulation model arose, and from which the system of partial difference equations of extreme scale algebra that governs, say, a petroleum reservoir simulation also arose. I theoretically discovered that I could go back to the root of the toughest problem in extreme scale computational physics. That root is some set of laws of physics. From that root of first principles or laws of physics, I reformulated the grand challenge initial boundary value problem of extreme scale computational physics called petroleum reservoir simulation, and I reformulated that problem to derive its governing system of partial differential equations. The paradigm shift is that my new system of partial differential equations is hyperbolic. The old system of partial differential equations that was taught to mathematical geophysicists and that was written in textbooks on porous media flows is parabolic. That paradigm shift or change from parabolic partial differential equations to hyperbolic partial differential equations changed the courant condition on the explicit finite difference algorithms that I invented and that gave rise to my companion partial difference approximations. My mathematical discovery of the early 1980s in Washington, D.C., United States, of that order of magnitude change in the courant condition allowed me to massively parallel process and to massively compress the time to solution and to compress that time by an order of magnitude. I'm Philip Emeagwali. I'm well known as a supercomputer scientist that invented a new supercomputer, but I'm not known well as a research mathematician that invented 9 partial differential equations of modern calculus. I was the cover story of top publications in mathematics, not because of my good looks. I was cover stories because I contributed to mathematics. One of my contributions to mathematics was that I invented how to discretize my new system of partial differential equations of modern calculus so that I can obtain a new and approximating system of partial difference equations of extreme scale algebra. My reformulated algebraic problem is diagonal, and with that new diagonal structure, my initial boundary value problem could be solved in parallel or solved across a new internet, that is a new global network of 2 raised to power 16 commonly available microprocessors. To put my contributions to extreme scale computational mathematics in a better perspective, it should be noted that the number of mathematical papers that could be written is infinite, but the number of mathematical algorithms that can be invented is finite. My contributions to the partial differential equations of modern calculus and to solving the extreme scale algebraic problems that arise in computational physics and to solving the extreme scale systems of partial difference equations of algebra and to solving those problems across a new internet that is a new global network of processors that were already available in the market was one of the few mathematical discoveries that were cover stories for mathematics publications. The cover story of the May 1990 issue of the Siam News, the top mathematics news journal, was on how I, Philip Emeagwali, invented how to solve 65,536 initial boundary value problems of modern calculus and invented how to solve them at once instead of solving them one initial boundary value problem at a time. My cover story of the May 1990 issue of the Siam News, the most widely read mathematics news journal, led to invitations for me to speak face to face and discuss my contributions to mathematics. I was invited to discuss my contributions with the foremost computational mathematicians. On July 8 and 9, 1991, and in my adopted hometown of Washington, D.C., United States, I presented the mathematical details of my contributions to the most extreme scaled partial difference equations of algebra. I presented the computational details of my contributions to solving those problems in parallel, or how I solved 65,536 algebraic problems at once. My contributions to the most extreme scaled partial difference equations of algebra arose from my contributions to partial differential equations of modern calculus. On July 8 and 9, 1991, I formally presented my contributions to mathematics, and I presented the 9 Philip Emeagwali partial differential equations of modern calculus that I invented, and I presented the new system of partial difference equations of extreme scale algebra that I formulated, and I presented both systems of equations before a standing room only audience of research mathematicians. My formal presentation of new mathematics to research mathematicians took place at 11 in the morning in the Dover Room of the Washington Sheraton Hotel, Washington, District of Columbia, United States. I formally presented my contributions of new mathematics to standing room only audience of research mathematicians that were attending the International Congress of Industrial and Applied Mathematics. At the end of my lecture on my new calculus, from which arose the largest system of partial difference equations of algebra ever solved, all the research mathematicians sitting in the standing room only Dover Room of the Washington Sheraton Hotel stood up and gave me a standing ovation. Like the Olympic Games, that conference holds once every 4 years and holds on different continents. That conference is the Olympics Games for research mathematicians. The speakers at that conference were research mathematicians that made contributions to mathematics. The speakers at that mathematics conference were like the gold medalists in research mathematics. As a speaker at that mathematics conference, I was like a gold medalist in algebra that was recognized for inventing new algebra, and a gold medalist in calculus that was recognized for inventing new calculus. At that mathematics conference, I spoke in the arcane language of research mathematicians. I used mathematical shorthands that enabled me to describe my contributions to calculus and to algebra, and to describe my mathematical contributions with only a few never before seen partial differential equations of modern calculus. After describing my new system of 9 coupled, nonlinear, time-dependent, and state-of-the-art partial differential equations of modern calculus that were hyperbolic instead of parabolic, I explained that my new system of 24 million diagonal partial difference equations of extreme scale algebra that was a world record in 1989, that was the toughest problem in extreme scale algebra, that arose from explicit finite difference approximations of hyperbolic partial differential equations, was not equivalent to the old system of tridiagonal equations of algebra that also arose from implicit finite difference approximations of parabolic partial differential equations that govern the motions of crude oil, injected water, and natural gas that flow across and a mile deep inside a porous medium, such as the Niger Delta oil fields of southeastern Nigeria. At that International Congress for Research Mathematicians, I explained that the polymath, that is a triple threat at the frontiers of knowledge in physics, mathematics, and supercomputing, looks beyond his blackboard, looks towards his motherboard, and looks across a new internet that is a new global network of 64 binary thousand motherboards. Unlike the research mathematician that only looks at his blackboard, the polymath looks across a new internet and did so to theoretically and experimentally discover that a system of diagonal equations of algebra that arose from solving a specific grand challenge problem in extreme scale computational physics need not be equivalent to the system of tridiagonal equations of algebra that also arose from solving the same specific problem in extreme scale computational physics. However, they both must solve equivalent problems in extreme scale computational physics and solve those problems correctly. They both must be equivalent in the governing set of laws of physics from which each system of equations of extreme scale algebra arose. In 1989, it made the news headlines that an African supercomputer wizard in Los Alamos, New Mexico, United States, had invented how to solve the largest system of partial difference equations arising in algebra. I, Philip Emeagwali, was that African supercomputer scientist that was in major US newspapers back in 1989 and thereafter. I was in the June 20, 1990 issue of the Wall Street Journal because I invented how to solve the toughest problems arising in extreme scale algebra. I invented how to solve initial boundary value problems of modern calculus and how to solve those problems across my new internet, that is a new global network of 64 binary thousand commonly available processors, or a global network of as many computers that were identical to each other, that were equal distances afar and apart from each other. It was across those 64 binary thousand processors that were already available in the market that I connected with the power of algebra. I, Philip Emeagwali, was that African supercomputer scientist that was in the news in 1989 and thereafter. I was in the news because I experimentally discovered how to solve a world record system of 24 million partial difference equations of algebra, and I discovered how to solve those algebraic problems across a world record number of commonly available processors, and how to process them in parallel or by processing many things or processes at once. And my invention opened the door to extreme scale algebra that arises in extreme scale computational physics. The system of equations that I invented were both differential and algebraic. My algebraic equations arose from my differential equations that arose from the laws of physics. Both systems of mathematical equations could be used to discover and recover otherwise undiscoverable and unrecoverable crude oil and natural gas. It's been said that there are more people living today than ever lived before. There are more scientists living today than ever lived before. A century ago, there were only 1,000 physicists in the world. Today, we have 1 million physicists in the world. 3 centuries and 3 decades ago, Isaac Newton did not describe himself as a scientist. The word science was unknown to Isaac Newton, who described himself as a natural philosopher. Isaac Newton's knowledge of mathematics is at the 6th grade level, and Isaac Newton lacks the mathematical maturity needed to understand the Philip Emeagwali's equations of modern calculus that was the cover story of the May 1990 issue of Siam News, that is the flagship publication of the research mathematics community. The Isaac Newton of the 17th century lacked the knowledge and the mathematical maturity that is needed to understand how to solve an initial boundary value problem of modern calculus. So our greater knowledge of our universe is what sets us apart from our scientific predecessors, and the most important contribution to our existing body of knowledge is the scientific discovery and the technological invention. We should distinguish between a discovery and applying that discovery, or distinguish between a discovery in physics and applying that discovery in engineering, or distinguish between a discovery in biology and applying that new knowledge in medicine, or distinguish between a scientific discovery and a technological invention. Using the modern supercomputer to discover otherwise undiscoverable crude oil and natural gas is merely a geological discovery, not a scientific discovery per se. The discovery of crude oil and natural gas is an application of the invention of the modern supercomputer that computes in parallel. For the research scientists and technologists to not discover and to not invent is to not contribute to human knowledge and is to slow down human progress. After arithmetic, calculus and algebra are the most important branches of mathematics. Calculus is the most powerful mathematical technique of all times. Yet, few people understand where calculus comes from and why and how calculus is even used to foresee otherwise unforeseeable global warming, or to deeply understand how the Philip Emeagwali equations can be discretized, coded, and message passed to 65,536 processors that shared nothing between each other and used to discover and recover otherwise undiscoverable and unrecoverable crude oil and natural gas. The system of coupled, nonlinear, time-dependent, and state-of-the-art partial differential equations of modern calculus, that is also known as Philip Emeagwali's equations, is used by first discretizing or approximating it to yield an extreme scale system of equations of algebra. Extreme scale algebra, arising from Philip Emeagwali's equations, demands extreme scale computations that in turn demands a network of millions upon millions of tightly coupled processors that shared nothing between each other, that defined and outlined the fastest massively parallel processing supercomputer in the world. Like new branches of mathematics, my new calculus arose from stimulations from the world of petroleum reservoir simulations, or simulating the motions of injected water, crude oil, and natural gas that flows from water injection wells towards crude oil production wells. That calculus is at the bedrock of such simulations, and that should not come as a surprise. The reason is that in calculus, the continuous motion is decomposed into discrete sequence of motions. In 1989, my invention of parallel processing attracted international attention and was in major US newspapers. My invention of the massively parallel processing supercomputer that occurred at 8:15 in the morning of Tuesday, the 4th of July, 1989, and that occurred in Los Alamos, New Mexico, United States, made the news headlines because that invention was the first time ever the speed of computation was instantaneously and experimentally increased and speeded up by a factor as large as 65,536. I attracted media attention because my invention of the massively parallel processing supercomputer yielded a measurable increase in the speed of computation that became my quantifiable contribution to the development of the modern supercomputer. I spoke directly with the media, and I did so to cut out the middleman scientist, to cut out the opportunistic scientist that contributed nothing to my invention but demands half of my invention credit and demands half of my invention earnings and demands them in exchange for nothing and in exchange for helping me tell and share my story. My 9 partial differential equations of modern calculus, called the Philip Emeagwali equations, and the companion partial difference equations of extreme scale algebra that approximated my 9 equations were not physical, never before seen objects that I invented. My new calculus and my new algebra were obstacles I overcame in my quest for the fastest massively parallel processing supercomputer. That new supercomputer was a new internet that was a new global network of 64 binary thousand tightly coupled, commonly available processors that shared nothing between each other. My new partial differential equations and my new partial difference algorithms were my new research instruments, and as much as my new processors and email wires. Sitting alone for a decade and programming alone the massively parallel processing supercomputer isn't child's play. In the 1980s, I wrote 65,536 supercomputer codes that each solved an initial boundary value problem that arose in extreme scale petroleum reservoir simulation. I message passed those supercomputer codes to my 2 raised to power 16 or 65,536 commonly available tightly coupled processors, with each processor operating its own operating system and with each processor having its own dedicated memory that shared nothing between each other. And I had as many 16-bit addressed emails that must traverse across my 16 times 2 raised to power 16 or 1,048,576 bidirectional email wires that I visualized as tightly encircling the 15-dimensional hypersurface of a hypersphere in a 16-dimensional hyperspace. In the mid-1980s, my invention was not recognized as an invention in supercomputing. It was only recognized as an invention after I broke speed records in both computation and communication. That invention is the Philip Emeagwali formula that then US President Bill Clinton reconfirmed in his White House speech of August 26, 2000. in 1989, my invention became a dramatic and a concrete confirmation that abstract equations and invincible algorithms could be simultaneously solved across a 16-network deep internet that emulates one cohesive supercomputer. The new equations that I invented and the new algorithms that I invented represented my theory, while the processors and email wires represented my experiments. Historically, the computer was a mathematics machine. The new equations on the blackboard and the new algorithms, or the new equations on the 64 binary thousand motherboards, were necessary and sufficient tools for recording my arrivals at the frontier of the new computer and the new internet. My goal was not to perform the fastest computation and fastest communication per se. My goal was not to solve my new partial differential equations and solve them to the 17th decimal place. My goal was to see the plural as the singular. My goal was to see 65,536 tightly coupled, commonly available processors that shared nothing between each other, and to see that ensemble of processors as one seamless, cohesive supercomputer that is 65,536 times faster than one computer that was powered by a processor that was not a member of an ensemble of processors. My goal was to see a 16-network deep internet and see that new internet as a small copy of the internet of the future that could become the planetary-sized supercomputer and become the new computer for your children's children. Thank you very much. Philip Emeagwali. Thank you.
Insightful and brilliant lecture. Insightful and brilliant lecture.